Hi guys, let's assume that you want to develop your own programming language, or you want to dig deeper into details how compilers are being developed, about their internal structure, libraries that are used to develop compilers, frameworks, and all other necessary components. In this video, I will explain you my vision of these compilers Iceberg. So let's melt down it together. First of all, you might ask yourself, what programming language should I choose to implement my language and a compiler for it? Or generally saying, what programming language fits best to accomplish this task? Well, historically, C++ was the main player on this field. However, what I see now, Rust is becoming more and more popular. Also, functional programming languages are well fit to develop compilers. For instance, OCaml or Haskell are very good for it. However, using them requires from developers to be familiar with functional programming paradigm, and it might be quite difficult. By the way, if you want to learn more about functional programming, let me know, so I will record a video. However, we are not limited with these possibly difficult languages per se. For instance, Tact, a smart contract programming language that is used in Ton blockchain, is implemented in TypeScript. And in fact, Tact developers responded with the positive feedback about TypeScript, that it feels quite good, and implement a compiler in it quite handy. So my recommendation here is not try to follow sort of best practice, but choose the language that you like and know. It will be the most profitable for you. The first phase in the compilation process is parsing. What you do on this path is you read a source code and make up an object model for convenient post-processing. Well, this part is performed by two components, a lexer and a tokenizer. Tokenizer splits the source code on individual discrete tokens and then upstreams them to the lexer. Lexer knows the language grammar and it can recognize patterns in the token stream and at the end produce what we called a concrete syntax tree. Concrete syntax tree is an object model that contains information in a raw style, meaning it has information about punctuation, tokens, and all symbols from the source code. You can implement both tokenizer and lexer yourself manually. It can take some time, but it's a very good practical task for deductive purpose. In industry, there are many already written and implemented what we call parser generators exist. The first one, or at least one of the first, was Bison. I'm not really familiar with. I know that it's more than 40 years old or something like that. Its successor was Yak, so maybe these people try to follow this naming pattern. Relatively new and widely used parser generator is called Antler 4 with grammar with the G4 standard or extension. What I feel about this standard, it's quite old and tries to follow old rules of defining grammar and respect them. Parser generator that I use in the inference project is Tree-Sitter. Tree-Sitter is quite modern, well developed, and it's currently under development actually, meaning new features and performance improvements are being delivered by the team. The grammar is defined in JavaScript in sort of functional way, so it's easy to read, understand, and amend. I recommend to use it personally. Parser generates parser according to their name for the target language. For instance, using Tree-Sitter you can target many languages such as Python, JavaScript, Rust, and many more. On this phase, you can detect grammar and syntax errors and immediately let developers know about them, because in fact there are a very limited number of analysis that you can do if the source code is broken. Of course, you want to include multiple files or libraries in one compilation unit. This task is being performed by a linker. Linker resolves, usings, includes, or name a few other directives that actually link other files into yours or link the project internal structures together. Well, what it does, it looks at the file system, or maybe you want to implement your language that will be able to resolve network includes it's up to you. So it resolves the actual location for the file and reads it and include into the compilation scope as a compilation unit. With the compound object as a compilation unit or module, it depends on how you name it in your compiler. You now are able to run different static analysis for the source code as a linter, or generally say as a static code analysis runner. So what you can find here is such things that you can determine without a need to actually execute the code. For instance, you can check when memory was allocated and released and find memory leaks. Also, you can try to predict racing conditions and other specific errors or problems that might occur in the source code. Using this tree-like structure, you're ready to generate what is called an intermediate representation. Intermediate representation is a language in between the source code and the machine code. You need an intermediate representation in order to be able to support multiple target compilation platforms. What I mean here is you want to be able to compile your source code for different machines architecture like x86 or RISC-V or ARM. LLVM, low-level virtual machine, is one of the most popular and well-known intermediate representation, and this is not only an intermediate representation itself, but a huge framework for compilers backend. It is equipped with a number of optimizations, and I think it supports the vast majority of possible compilation platforms. MLIR is another popular intermediate representation framework. It supports multiple dialects, so you can define your own, as well as you can define reusable transformation passes. Before being ended up with the machine code, compilers or intermediate representation frameworks perform different optimizations on the source code. There are many different optimizations that can happen, for instance, inlining or dead code elimination, loops, unwilling, etc. They can be very tricky though, and you need to keep in mind one thing here. Since you optimize your code, you change it. And if you change the source code, it means that you can accidentally change the semantics. And if it happens, it means that you introduce code behavior that was not intended by developers. And you need to be careful here. So either review multiple times your optimizations or use only those that you're particularly can rely on. Before discussing the part which is related to machine code emission, let's briefly touch the NanoPass framework. The NanoPass framework says that you need to design your compiler in a way to segregate internal passes in your compiler into small and granular procedures. Each procedure takes an intermediate representation and returns an amended version of an intermediate representation saying IR to IR prime. This allows you to be able to focus in on particular passes, improve them, and it makes a collaborative work on the compiler easier. In big compilers, there could be hundreds of passes. To define a machine language standard, an instruction set architecture is used. It describes how a particular platform works with memory, input, output, and other standard components of the system. For virtual machines, the story is a little bit different. Virtual machine has its instruction set of a list of opcodes, operational codes. So if you target a virtual machine, you need to emit these opcodes, and the rest you're not really care about. Meaning, particular virtual machine version will be compiled for the target platform, and it will propagate your opcodes to machine codes transparently for you. In blockchains, virtual machines are used. Ethereum uses EVM, Ethereum virtual machine with dedicated opcode sets. Other blockchains, many of them, uses WASM-based virtual machines. They amend WASM command set with specific opcodes that they need to implement particular blockchain functionality. In inference, we amend WASM standard opcode set and introduce their non-deterministic instructions. If you want to take a look, please follow us on Twitter, and you can find there in our organization a repository with WASM tools where you can find how we intervent our non-deterministic commands into the WASM instruction set. The last bit in my narration, but not the least in real life, is you need to maintain your language live during the process of development and after that, of course. You need to provide a set of tools for developers to make their life with your language easy. You need to develop a debugger, a package manager, and other convenient tools. Also, the standard library is crucial. I think no one wants to implement everything from the scratch every time. So the richest library you have, the better for end users. And of course, the community is important. You need to have people that will work and use your language. So attracting people from the very early stage is important, I think. What we do and what I encourage everyone to follow is an open source style in your development and approach in such things. Because languages are kind of public good, which everyone should use, can use, and the more people are involved, the better for the project. That's why I'm recording such videos, so I encourage you to join us on Discord server so we can chat there. Okay, many bits we have covered in this video. Keep in mind, everything I said is my experience, my research, and my thoughts on the topic of compilers development. So if you like it, please follow us on GitHub and join our Discord server. See you in the next video.